Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only 3 nodes, x, y, z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. Yeah. In node x, okay, the distance vector of x is initialized this way. For destination x, well, it's itself, therefore, distance 0, it does not cost anything, okay, to transfer data from x to x. To go from x to y, let's initialize it to the link cost of xy if they are adjacent to each other. So 2 here. xz, so xz, they're adjacent, therefore we use the link cost between xz. Okay. Similarly, you do the same thing to initialize dy for node y, dz for node z. Now, hey, in node x, it maintains all neighbors' distance vector, alright, but at the initialization phase, node x did not receive anything from y nor from z yet, so dy and dz, these two vectors, are left null. Okay, so I'm just using the sign of infinity there, okay, to represent their null. Similarly, for dx and dz in node y, and so on and so forth. So this is how you initialize, okay, the initial distance vector table, which is composed of 3 vectors. Okay. You maintain your own vector, you maintain also the neighbor's vector. Now, once, okay, the vectors are initialized, each router will what? Okay, notify the neighbors. So this vector here will be sent from x to all the neighbors, y and z. Similarly, node y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, okay, in the next cycle, node x here in the table, it's going to see dy from node y, dz here from node z. All right. Now, with neighbors distance vector in place, now we can begin to calculate the dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-Ford equation says we try through all the neighbors, okay, of the source. X is right here, the source, 2 neighbors, y and z. So yeah, we do have 2 entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0. Okay, as dy y says 0. Link cost xy, 2. So 2 here. Now, for the second neighbor, z, link cost of xz, 7. So 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y. Right here, it says 1. So 7 plus 1. This is 8. And this is 2 only. Therefore, y here wins. Okay, y is the next hub router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz. Okay, so from x to z. Again, from the same source, two possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. The shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. To go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, no y there is going to be calculating the dy. No z there is going to be calculating the dz because it's receiving dx and dy.